Good morning and good afternoon. I would like to thank the organizing committee for the invitation for this presentation. My name is Jyh-Chin Juang and I'm from Department of Electrical Engineering, National Cheng Kung University, Taiwan. The topic today is about the development and flight result of the IRISA CubeSat, and it was a CubeSat that is development at National Cheng Kung University. Let me start this presentation by introducing National Cheng Kung University. The university is located at Tainan City, Taiwan, and it was established in 1931, so it's more than 90 years. And the university had 10 colleges, that's including all the engineering and also science and even medical college. And the university had more than 20,000 students, and for the full-time faculty members, it's about 1,500. And the university has several departments and colleges that's related to space science and space engineering. That includes College of Engineering, College of Electrical Engineering and Computer Science, which I belong to, and also College of Science, among many others. Between NCKU and Georgia Tech, I think we have a long and good friendship in the past. Indeed, between the two universities, there is an active MOU between, so that we have been some cooperation in different disciplines. And in the slide, you can see certain when the dean of the College of Engineering visited Georgia Tech about 2 years ago. That's before the pandemic. The CubeSat is indeed a many active subjects in the space industry, and also it has been regarded as a many useful tool to educate students. So at NCKU, which is noted for its engineering, many good engineering school. So we have been involved in CubeSat for more than 10 years. And in this slide, you can see some of the CubeSats that have been developed. That's including the PACE, Phoenix, Birdie, IDEASSat, and IRIS. And so we started this kind of activity in 2003, which many close to the beginning of the CubeSat, and ever since we have been combined lecture, that's in classroom, and research laboratory together. So we try to advance the space-related technology, and also we try to put into a curriculum so that we can educate students to be involved in this subject. And the PACE, Phoenix, and IRIS have been launched. So on the left, you can see all the NORAD ID of this CubeSat. And today's topic is about IRIS, which is a project or the CubeSat that we've been working on in the past few years. But before I talk about IRIS in detail, I would like to review some accomplishment about the Phoenix. Phoenix is a part of the QV50 project. The project itself is a European project for establishing an international network of about 50 CubeSats for multi-point in situ measurement in the low atmosphere and re-entry research. And the project time span was 2011 up to 2017, and it was coordinated by Montcalm Institute at Belgium. And the objective of the QV50 project was to facilitating access to space, so that's to encourage research organization and university to participate this kind of activity, and then they could build CubeSat and also launch the CubeSat. And as there have been several payloads that's been considered in this CubeSat project, so that lots of in-orbit demonstration are regarded as many important to enhance the so-called TRL, and also it has served the purpose of education as well as scientific research. Overall, 36 CubeSats have been launched, and NCKU Phoenix is one of these 36 CubeSats that were launched as a QV50 project. And I would like to use one slide to summarize what has been done in this Phoenix project, because we believe that is indeed have been a many important cornerstone in the development of CubeSat in Taiwan. It's because of the success of this Phoenix, the National Space Organization, they pay attention to the CubeSat research, and some commercial companies, they begin to aware of the potential of the space industry. So that's indeed a turning point for the human resource accumulation, and also for the focus of the potential of this kind of technology. Okay, the project started in 2012. That's just after when Montgomery Institute announced the opportunity. So we begin the design in 2012, and then we do the assembly in 2013 to 14, and then integration 1 year later. And then in 2015 to 2016, there's a lot of tests have been done. That's including thermal vacuum tests, vibration tests, shock tests, and also end-to-end tests, and even the long-range communication tests. And in 2016, we deliver the CubeSat to Montgomery Institute, and indeed to the launch site. And then the CubeSat was launched in 2017, and it was a piggyback launch, and it's a relay launch. That means the launch was sent to the International Space Station, and then afterwards it was released from the International Space Station. And so it's essentially a 400 kilometer altitude when it was released. And the team, the NCKU team, has been able to make a contact following the release, and then we have operated this CubeSat for about 2 years, and the satellite that eventually re-enter into the atmosphere, and it's among the latest one. That means among the 36 CubeSat we stand there for some time, and then we have accumulated many important scientific data as well as in orbit CubeSat data. So that's have been a many important research results, and for us to advance further. And I would like then to talk about the project that we have been working on in the past couple of years. That's a project that's starting from 2018 to 2021. And it was a project sponsored by MOST, which stands for Ministry of Science and Technology Taiwan. And because of the activity, space-related activity internationally, so that means the MOST, they begin to turn their focus in the certain potential for so-called space industry. So they start this project, key technology of space industry project, in the hope that it could promote R&D activity, and it also can establish domestic capability of key know-how for space industry. And more importantly, it's regards system integration and flight validation are important. So these two subjects are emphasized to showcase the complete competitiveness in Taiwan space industry. And so with this in mind, the goal of this project, or the key technology of space industry project, are to promote practical application of academic research to space industry, foster R&D scientists and engineering for key space technology, and integrating domestic research capacity of space technology, including academia and research institute. And at the time of 2018, it was a time when Taiwan was planning for the so-called Phase 3 National Space Strategic Projects. So it was also hoped that this project can in line with the Phase 3 National Space Strategic Project, so that certain technology can then be built up, and also some common goal can then be accomplished together. So the IRIS is a project that come out from the up mentioned project. It's a CubeSat project, and the objectives are to design, manufacture, test, launch, and operate CubeSat to pave the foundation for domestic space industry. So essentially, that we echo the requirement or the desire from the MOST. And we think CubeSat is a very important platform for the technology development as well as the system integration. And within this IRIS CubeSat project, we're looking for three things, or we divide into three sub-projects. One is intelligent remote sensing. Okay, remote sensing definitely is a very important subject in the application of CubeSat. But if you are talking about using CubeSat to take picture or do remote sensing, definitely you are bounded because your spatial resolution cannot be too good. Also, the data volume or the data bandwidth that you can be transmitted is so sometimes very limited. So we will hope that we can build some smart technology on board the spacecraft. And so that's when during the observation, it could do certain screening by using edge computer and deep learning technique. For example, it could classify the object, so that's only interest object can be singled out, and it could remove cloud and some other application. And this the certain sub-project that we're interested in, we call the Internet of Space thing. That is at the beginning of the lots of space communication, or another web of space communication. And it's regarded that space is an important environment for seamless communication, especially for internet connection. And we look for the Internet of Space thing. That means regard the CubeSat as a node in the internet, and so that it could send and receive certain data so that you can form part of the network. And in doing so, because this kind of space object or this node are moving, so we need to have a good control or understanding of the position and time of this kind of node. So in doing so, that we also develop certain navigation technique as well as a timekeeping technique in this space object or space things. Finally, there's a subject that we are looking to. That's a force tolerance control. And the motivation for this is simple, because lots of CubeSat or even SmallSat, they are manufactured by using the cost component, the commercial off-the-shelf component. And the reliability of this component may be low because you have to consider your costs. But if you can somehow, or if we can somehow develop some technology that could tolerate a certain failure or detect the faults of this component, in that case, we might be able to do something interesting. So that's we look into by using intelligent control and to perform some innovative fault tolerance control. And with this consideration in mind, we come up with the so-called IRIS CubeSat project. And the project scope is as follows. The IRIS, the spelling is Intelligent Remote Sensing and Internet Satellite. So it's encompasses the remote sensing and Internet objective of the CubeSat, but also covers the intelligent fault tolerant control subject. So that's we named the project as IRIS. And to fulfill the goal, we look into two CubeSat because the mission objective of the remote sensing and internet are not totally identical. So we divide into two CubeSat. One we name as a IRIS-A, which is a 2U CubeSat, and it's for the IOT experiments. Another is IRIS-B, which is a 3U CubeSat for intelligent remote sensing. And the operation scenario or concept operation is as follows. For example, for the remote sensing or IRIS-B CubeSat, the satellite after the launch and stabilization, it could then take picture of the interest site. And then there's an onboard processor that could extract certain feature which will be interesting, and then it will then download this feature only instead of the whole picture, because sometimes if you want to download the whole picture, it takes time, and sometimes if this picture or this image does not contain too much information. So we would like to do certain screening or certain inference on board the spacecraft, so that we can transmit interest information to the ground. So the organizational project is as follows. So 3 universities have been involved in this project, that's including NCKU, NCNU, and AFATS. NCKU, a National Qinghai University, which is a university located in Puli, Taiwan. And AFATS is Air Force Research University, and it's located in Gangshan, Taiwan. Okay, so 3 universities. NCKU is the prime contractor of this project. And to fulfill the requirement of the MOST project, we also invite some industrial partners to join the project. And based on our previous relationship in this project, we also have some international partners. So the main project is responsible by myself, and there's a sub-project 1, which in which Professor Lee take care of all related activity, and the sub-project 3, Professor So is responsible for that, and I also take care of the sub-project 2. Okay, so if you look at the IRIS, you can see the IRIS Bastin, and also there are 2 payloads. One is IoT payload, another is a small smart remote sensing payload. So we have the goal that we share the same bus technology. So same bus technology, but that can serve for remote sensing application and Internet of application. And the bus technology definitely coming from, for example, the main project as well as some intelligent fault-tolerant kind of control technology. And as NCKU is responsible for the integration. And also there are some domestic industry partners, that's including Lescotec and Lescom. They help us and then cooperate with us to develop some technology. And among the international partners, that we have been cooperating with QTech and University of Philippines in this project. And definitely, as NSPO is a main space agency in Taiwan, we also cooperate with them because we could get some remote sensing data from them. We could cooperate with them to gain certain know-how. And so that's a certain knowledge from NSPO is also mainly valuable for the execution of the projects. Let me start with the Internet of Space Things. The Internet of Space is sometimes being referred to as the Internet of Space. And essentially, if you look at the development of the communication system or mobile communication system, especially in the future, we are talking about beyond 5G and 6G communication. A lot of so-called non-terrestrial network has appeared. So that's including using unmanned vehicle, high-altitude platform, as well as satellite to serve as a communication link. So that's all the internet can be seamlessly connected, and then you will have no gap in time or in location. So this is a trend, and it's an important major business opportunity in the future 3GPP plan. And to fulfill this goal, definitely satellite will play an important role. But when we talk about the satellite, we have to think about satellite in different sizes. For example, you can have stationary communication satellite that can have a large bandwidth. You can have communication satellites such as Starlink and OneWeb satellite that can also fulfill some internet connection. And for CubeSat, definitely we realize that its capability is definitely limited. So we look into for the so-called IOT mission, the Internet of Things. That means it could provide communication and internet service, but we realize that the data amount will not be too significant, and the data rate definitely can be relatively low. But as long as the requirement is to fulfill certain communication, this kind of IoT can also provide some data for information exchange. So we focus on the so-called low bandwidth and low data rate kind of transmission. And to do that, definitely we survey a lot of IoT technology, and including its frequency regulation, including its data rate, as well as the communication range and so forth. And we realize that LoRa or long-range communication can be the most applicable one. So therefore, we adopt LoRa technology into our IRIS CubeSat. But also we realize when we do IoT mission in space, definitely, and we have to recall the position of the communication node or the CubeSat as well as the time. So therefore, we come up with certain design that have a better navigation as well as a timing accuracy. So with that, we hope to come up with an integrated solution that's including the navigation, timing, and communication, so that it could serve as any intelligent node in the future IoT or in the future iOS. And this particular IoT payload is developed, tested, and verified in the IRISA. So to take the concept operation of the IRISA is IoT mission. So the IoT mission can be stated as a so-called store and forward. That's when you have a lot of remote terminal, the ground terminal, and sensor. And this sensor can collect certain data, for example, humidity data and air pollution data and so forth. And then through the ground terminal, this data can then send it to the satellite when the satellite is overhead. And then when the satellite moves, and then when it's above the ground station, it could then download the data. So that means it could store the data for a certain period of time and then forward this data to the cloud server and the user. In doing so, definitely this satellite had to, when it collects the data, it had to be aware of when and where. Okay, so and in doing so, that's when we're doing this kind of IoT payload verification. We integrate GPS receiver and atomic clock into it. So the IoT payload essentially an integrated sensor suite that's including the communication, navigation, and timing module. The IRISA CubeSat is a 2U CubeSat, as I mentioned, and this view graph briefly talk about some main characteristic of this CubeSat. And the structure definitely we follow the CubeSat standard, and it's less than 3 kilograms. And the thermal essentially is passive monitoring, but we also have active control of the battery to make sure that the battery will not be too cold. And the power itself is generated by the solar cell, and we have 32 solar cells overall, and there are 4 lithium battery for the power storage or the energy storage. And the average power generated in the nominal orbit is about 5.7 watts. Okay. And the communication that we rely UV band, we rely UHF band for downlink, and then the VHF band for, sorry, that's uplink. Okay, this is uplink, sorry. And the downlink rate is 9,600 bps. The attitude control, we have a module within it, so the knowledge is about 1 degree, and the control accuracy is 3 degrees. Okay, the computer itself, we have 2 computers within this CubeSat, and there's an online processor, and then there's a Cortex-M3 processor to fulfill all the data handling and then the task. And for the payload, as I mentioned, is an IoT payload. This figure shows the IRISA configuration. So it's a 2U CubeSat. So that means if you look at the size, it's a 10 centimeter, 10 centimeter. This is about 20 centimeter. Okay, and all the ingredients are there, so you can see all the circuit module. And we have a buy and make policy. That means we purchase some existing module, but also we also make some circuit module to do the integration. And that's this module, as you can imagine, that's including the power, the computer, the attitude control, and among communication and so forth. A more detailed look of this module is in the figure here, so that we can take a look at the organization. So if you look from this side, on the left side, you can see all the solar cell, and this integrated into the system, and definitely through this kind of wiring, then we can then connect to the electrical power subsystem, and then the power subsystem definitely will do the power regulation, conversion, and distribution, and so forth. And also there's also ADCS module that's could do the attitude control, and the attitude control definitely have certain sensor, and the sensor including magnetometer and also earth sensor as well as the sun sensor, so it could determine the attitude, and it also can also use a magnetic torquer and wheel to do the attitude control. And then there's also an OBC, that means the computer system, so that's responsible for all the data handling of the system. That's including storage and then the main routine to do the operation. And to make things more interesting, we also have another circuit board. That means we also have a circuit board that has a certain interface, some specific payload, and also there's also a communication board. Okay, the communication board responsible for the demodulation and modulation and other tasks. And finally, there's also the payload interface. So that's we had to integrate the payload together. So overall, you can see the overall organization of this. And as I mentioned, some of these modules are purchased from existing vendor, but we had to develop and then integrate lots of something else together and to come up with a system. It's interesting to take a look at the payload. Okay, the payload, as I say, is the IoT payload that's including the communication, which is realized by the Loren receiver, and also a navigation module. The navigation module is a GPS receiver, and this particular GPS receiver is an NSPO design. That means it was inherited from the National Space Organization, and then we included into our CubeSat. And there is also an atomic clock module, and so we integrate the clock and navigation as well as the LoRa module and together. And definitely we had to do a lot of engineering development and tests to make sure that the sensor data, once collected, can be appropriate tagged, and then make sure that's, for example, the GPS timing and then the atomic clock timing, they are synchronous to each other, and so forth. So there's a lot of activity being conducted in to realize this as a unified IoT payload. The IoT payload that I mentioned was in space. So in the counterpart, we have also to have a ground terminal to, for example, to collect the information and send the information to the CubeSat. And this is a ground terminal that we have developed to doing this. So essentially, that's the circuit board there, and also the transmitter there. And to make it operate in the remote side, we also have a certain power module so that it could operate independently. And definitely we have a home antenna for the transmission. So this is compatible with the space units. So that means we can then install this at a remote site and then to collect interesting information to realize the communication task. So in the scenario, this ground terminal can be set at an interested site, so you could then collect the sensor data, and then once there's a path, this information will then be transmitted to the CubeSat, and the CubeSat can then collect that and store for some time, and then forward to the user. So as mentioned, that we started development in 2018. So we have developed this CubeSat, and these are some of the photos that you can see. That means including some engineering markup, and then the table satellite, and also there's a test for the ADCS, and also this integration as well as the solar cell, and then this for the end-to-end test. So video, sorry, there are some rendering, but just use a video to let you see some of the activity that's being conducted. This is part of the ground station. So after we finish all the development and tests, then finally it's time to launch. The IRISA was launched on this year, January 13th, and it's part of SpaceX Falcon 9 Transporter 3. And so it was launched and on January 13th, and then on the next day, we have been able to make a contact, and this information, all the telemetry data that we receive, and then it's immediately verified that's it coming from the IRISA CubeSat. And ever since, the satellite has been successfully operating. And these are the figure from the amateur radio tracking station. So you can see some information, and definitely if you're interested in the CubeSat, you can also find some additional information there. And you can see also our badge. And the operation scenario is like this. So there's a update and counting from the ground station. So the main ground station is located at NCKU campus, and we have the ground station at our campus, and so but we can also operate this ground station remotely, and so they can operate this CubeSat in the day-to-day basis. And for the IOT experiment, that we could then install this terminal anywhere, and then it could then send through the LoRa mesh up to the CubeSat, and then forward to the ground station. I would like to take this opportunity to introduce Starcast. And this is a ground station control and operation software That's it developed in-house when we're doing or conducting this IRIS project. And this Starcast is a feature a lot of things that we turn out to be in many convenience for the control and operation of the ground station. That's including scheduling and also including radio and antenna control. And it could also have a good or streamline all the tail command and telemetry kind of data automatically. And definitely all the data or all the tail command that you send have been archived. So this is, you can see different kind of screenshots, and that's good, and it contains several, pages so that you can see, for example, the telemetry, and then monitor the ground station, monitor the transmitter, TNC, and so forth, and even monitor the orbit. So that means it's many convenience tool that we develop this, and when we operate our IRISA CubeSat, we further refine this Starcast, and I think it's have been much mature now. Okay. In terms of payload validation, definitely we have done something ever since January. One of the activities that we have accomplished is to verify or validate the GPS receiver. As I said, that's in the IRISA CubeSat that we install the GPS receiver. That receiver, frankly, was not flight proven. That's mean in the past it's developed at a laboratory, but it haven't been flown in the past. And we are lucky and we are happy that we flew this GPS receiver and we verify its performance and validate its performance. And so this is granted. So that's in Taiwan. So the satellite is going this way, and we send a command, and then it's able to do the fix, and then it report the position. And the position was closely to the two-line element at the very beginning of the orbit, because as I mentioned, the satellite was launched in January 13, and we have been able to do this in January 20, about 1 week later. And there are also some IoT experiments we have been able to accomplish so far. And within the IRISA, there's also a digipeater. The digipeater, instead of LoRa, can from the ground station to ground station kind of a store and forward. Okay, so within our CubeSat, that we have a certain procedure that can allow we to do this. That means instead of from a remote ground terminal, we can then from another ground station send certain messages, and then that could then be forwarded to our ground station. And this has been verified with some amateur radio, and we are now also working on the LoRa, and we hope to come up with some other result about this in the future. As I mentioned, the IRIS, including IRISA, which is IOT mission, and also there's also remote sensing mission, which is IRIS-B. Okay, and there are some common between IRISA and IRIS-B. That means essentially they share the same bus. Okay, but definitely the payload are not the same. Okay, so the IRIS-B, the mission is remote sensing, and remote sensing definitely is an important subject, including indeed many different mega constellations have been developed to try to do this kind of remote sensing, and then emphasize on high spatial and high temporal resolution, and also multi-spectrum constellation and so forth. We look into the intelligent part of the remote sensing. That's when we try to enhance the sensor so that it becomes smarter than others. And that's because in Taiwan, that's one of our industry strengths is information and computer technology. So we know how to make things small, and we also how to make things smart. And we believe that with some research in this direction, that we could come up with certain space heritage that's unique. So the objective of the IRIS-B remote sensing mission is to develop and verify the intelligent edge computer, and by using CubeSat. And the bus itself has some similarity with IRISA, but definitely also some variation, because if you want to do remote sensing, you may need some additional power, especially you have an edge computer on board. So the number of solar cells is greater, and also in the ADCS module there's a star tracker, because we would like to have a better pointing accuracy, and also because the image data definitely is the volume is kind of large, so we utilize S-band for the data transmission. And these are the payloads that have been developed in this project. And as you can see, that we utilize the lens from the customer existing lens, and then we try to do some work so that it can be outfit into the CubeSat. And among that, there's a structure that has been developed try to hold this camera and also circuit board. And all these circuit board are in-house developed, and then definitely we try to develop this kind of circuit board so that you can eventually have all the technology in hand. And the target requirement for this picture taking is to have a spatial resolution about 8 meters at 100 kilometers, and the swath is in the range of 10 to 20 kilometers. And the important part is within this board there's a deep learning network, so that we have a network that could do some inference and classification task, so that the image once captured could be processed, and then it can then be, for example, can store and then downlink, or it can be thrown away if we realize that does not contain interesting information. Okay, so definitely to do that, we had to train our network, and also there's a requirement that when we implement this in space, definitely it cannot be too heavy. So we have a lightweight network being developed, and definitely a lot of ground tests are needed. So this view talk more about the IRIS payload B. That's including the camera, and there's a 3 major board that's including the image capture. So that's essentially CMOS sensor mean capture, and then the data is stored and then forward to this so-called image data operation board to do the inference. And once the inference data, and then it's will then through the communication board, and then this become the interface between the satellite bus and the remote sensing module, and the data can then be sent to the CubeSat, and the data can then be downloaded. So there's a lot of decision making within this 3 board there, and that's this 3 board have been developed, and then we have been verified this board already. And definitely, if we want to do the so-called remote sensing smartly, we have to ask ourselves a question: what kind of object that we are detecting? Okay, so for that, definitely we interested in the so-called lens style and debris flow kind of image. That means we take a picture and then we try to detect whether the region is subject to lens style and debris flow, because one objective of this kind of remote sensing, especially the application scenario that we can think about, is if you have a satellite that can do this kind of detection, that could have a many important societal impact. So to do that, we utilize NASA USGS data, and then we essentially look into those data, and definitely we're looking to do data collection. That means there are some data that related to lens style and debris flow. So we pick those data out for our purpose of training. And this kind of data, together with some NSPO for most asset data, we can use that to do the training of the network. And this network can definitely, after training, it could then uplink to the satellite, and satellite can then do the inference in space. And there are some features that have been developed in our network, that's including we use some spatial feature extraction and signal processing scheme. And this is for the debris flow and then star detection in space. So essentially that means when the data satellite capture the image, it do certain processing, and then through this inference network, which is a tiny mobile net V2, and then it could then release some information or some feature related to lens size and also to the debris flow. And with that, we can then select those data for download. And definitely this will have to come up with a closed loop. That means we can then have a potential to keep refining this network. So essentially we have this in mind. So that's when we come up with the overall development flow. So that's we could then utilize that to refine our network in space. So hopefully that's good visual training. And with this in mind, definitely that's this particular network can also serve other purpose. For example, we train this for the detection of lens size and debris flow, and it could also be trained for example, to remove the cloud or and so on. And in doing so, we face lots of design considerations. So I would like to share with you about this. And because we had to implement this smart remote sensing in space, so we had to trade off among computation, power, and data communication. Computation, definitely, we can, as we know, we can have a many comprehensive neural network, but that's typical take a great deal of computational resources and also demand some power. Okay, and also there's also consideration of data communication, because each image will take some time to do the transmission. So the way that we do that, we come up with some image partition scheme, and then we do some of this in parallel, and then we have been able to fulfill the requirement of the 3 frames per second, and by this kind of partitioning. An activity that we do the verification is using the UAV to do a test. So we install the camera and all the circuit board as a UAV, and then we take the picture and then verify the processing capability as a UAV. So that's have been done, and then we have been able to accomplish this kind of result. This, frankly speaking, is acceptable for our application. Definitely, we have to control different kind of parameter. Okay, but this essentially verify the functionality of the system. And we look forward for further development of IRIS-B and eventually the launch of the IRIS-B. Finally, I would like to talk about the fault-tolerant control. Fault-tolerant control is an important subject, and typically this kind of fault-tolerant control is applicable to large satellites. But we believe that with so many commercial off-the-shelf components being utilized in the small satellite and CubeSat, some fault-tolerant control may be needed. Okay, but the challenge in fault-tolerant control is if you're talking about from the, for example, using neural network or deep learning network, you face the problem that you do not have sufficient amount of training data. So that's we utilize the so-called generative adversary network kind of scheme, try to come up with the data and then for the training. So in this kind of so-called GAN network, there's a generative and then there's a discriminator, 2 type of network. And then they do the training, and then we have utilized the satellite attitude control subsystem as a module, as a target for this kind of verification. And so this is, again, that's an ongoing work, and then definitely we hope that this kind of network can then be, for example, become lightweight and after the training, and then can be utilized in space. I have mentioned the MOST Key Technological Space Development Project, and in this project, the MOST called for the involvement of local industry in the space project. And from my point of view, my perspective, IRIS has fulfilled from the space industry, for the space industry, and to the space industry kind of requirement. From the space industry, because in the project we have cooperated with local industry, that includes Lescotec and Lescon, and we cooperate closely with them. Lescotec is responsible for some circuit module and remote sensing payload. Lescon is helping us in one of the LoRa module. And for the space industry, that means after the launch and operation of the IRISA CubeSat, some key and innovative technology have been verified. That's including this kind of edge computer and lightweight AI. And also we have validated the GPS receiver. And we also verified the Starcast ground control software, ground station control software. And for the space industry, that's even more important because the team or some of the team members had joined the startup Talos Interstellar, and they are now many active members in Taiwan to pursue the space commercialization and in this part. So I believe that's when we talk about the project outcome, and we have many outcomes that's many encouraging. The Space Laboratory at NCKU, together with other department and college as NCKU, we have been involved in CubeSat research and the social educating task. And in this presentation, I talk about the IRIS project that's including the IoT intelligent remote sensing and payload. And some experiments are ongoing, and I hope that in the future I have opportunity to share with you. I would like to end my presentation by acknowledging some of our team members, and I put this in the Chinese because that can be more easily recognized from TSU. And I would also like to acknowledge IRISA Taiwan, as I'm the coordinator of IRISA Taiwan. We hope that's to promote the space education and then all related activity related to space. And with that, I thank you for your attention.